Okay, I'll turn the light back off. If you can write that down, rate of change momentum and rocket science. Okay, you got that written down? Yeah? So, another way to state Newton's second law is F equals delta P over delta T, but we'll have to explain what each part means. Delta P is what's called the change in momentum, and delta T, of course, is the time. But we have to define what momentum is now, and I'm sure some of you know what momentum is. Yeah? Does anyone know momentum? Nearly perfect. Nearly. Not quite that complicated. Abdul Ali, no, Rahman, was close. We just had one word wrong. Yeah, yeah. But he gave me one word wrong. The product of mass and velocity. Momentum has a sign. It could be plus or minus. P equals mv. With the units, of course, as kilogram meters per second. Now, what I want to do next is give you a proof to show you that this formula is the same as F equals ma. Can you all see? You all see? Ming, can you see? Yeah. Yeah? You got that? Yeah? No? Okay. Yeah? Continue? Okay. So, let's give the proof now. So you have F equals delta P over delta T. The time is T. And the delta P is the change in momentum. So this is the momentum at the end, and this is the momentum at the start. Well, I can take the m out, and I get v minus u over t. Or actually, I can keep it as delta t. It makes it a bit clearer. Because on the top, this is the change in the velocity, which we can call delta v over delta t. Now, I think it should be clear what this is. Yeah. Yeah. So you can see it's the same. Same result. So F equals ma is really the same thing as saying F equals delta P over delta T. Now in the exam, they might ask you to prove that. I should tell you when they ask you for what's Newton's second law, they prefer when students give this form of the law. They like this version better than this version. The reason for that, I think, is because this was Newton's original way of putting it in his book. Force is the change in momentum per change in time. Yeah? So just try to make note of that this is the preferred version in the exam. Exam preferred. Okay, you got that? Yeah, continue? Yeah, okay. So why bother with F equals ma if the other formula works? Well, the other formula is actually very convenient when the force being applied is for a small time or when we want to calculate something called the impulse. Anyways, the impulse, well, does anyone know what the impulse is? Yeah? Yeah, but what is that? Oh, thank you. Impulse, yeah, that's true. Impulse is the change of momentum. That is, impulse is delta P, which is the same as what you said. Okay, did you write that down? Yeah? Okay. So here's a simple enough question. I think you can do this quite easily. A 1,200 kilogram car crashes into a wall at a speed of 20 and is brought to rest. What was the impulse on the car? It should only take you a few seconds to calculate. So if you can calculate that. You got that? Yeah? Right. So let's have a look at the answer here. The impulse is the change in momentum, which is mv minus mu, which is, what did we say the m was? 1200, wasn't it? Yes. And the v, 0. And the u, 20. So the answer is minus 24000, isn't it? 3 O's. Don't forget the unit. Kilogram meters per second. Don't forget the unit. Did you forget the unit, Jason? No, sorry. Peter. I'm mixing people's names up today. Did you forget the unit? Okay, continue. Yeah? A hammer hits a 100-gram nail with a force of 50 newtons and the nail moves with a velocity of 4 meters per second. For how long was the force applied to the nail by the hammer? So this formula, or this problem, you'll need the formula F equals delta P over delta T. Now, It's possible that you could use F equals ma as well, but I think you'll find it's easier if you use F equals delta p over delta t, and I am looking for the delta t. Give that a try now. Okay, you got that? Yeah? So let's have a look here. F equals delta P over delta T. So delta T equals delta P over F, right? Which equals MV minus MU over delta T. What's the M here? It's 0.1. What's the V? It's 4. And the nail started obviously at rest until the hammer struck it. Sorry, I meant to write F here. And the F we said is 50. So that's 0.4 over 50, isn't it? Which is 0.008, is it? Do I have the right number of zeros? Yeah. Which is 8 milliseconds. Okay, you got that? It's okay? Yeah? Now, a 250-gram football's at rest. A football player kicks the ball and the ball moves away with a speed of 10. Work out the impulse, and then the player's foot is in contact with the ball for 100 milliseconds. What was the force applied to the ball? Okay, so here's another short one for you to try. Then I think we have something harder to go on to after that. Yeah, so give me this answer, please. Okay, you got that done? Yeah? You got that done? Right. I should have it done by now. So impulse is delta P, which is MV minus MU. In this story, the U is 0 because the ball will be at rest. The M Yeah, that's it. And the V, 10. So that's 2.5 kilogram meters per second. And then the next part is what's the force?
2.5 over.
Yeah. Delta
We
P
change it
over
to-
delta T. And I'm looking for, yeah, okay, so it's 2.5 over 0.1, isn't it? 25 newtons? Yeah? Yeah?
Yeah.
Yeah, it was 100 milliseconds.
So 100 milliseconds. 1 second is equals to 100 milliseconds.
1 second equals 1,000 milliseconds. Yeah? Is okay, Kehan?
Yeah, it's the letter P has another meaning, such as the rate of work.
That's capital P. This is a small p. Yeah, it can be confusing. Yeah. Yeah, I know. How am I supposed to draw the difference between a big and a small p? Okay, continue. The biggest advantage to using the formula F equals delta P over delta T is that it allows you to calculate the force rockets have. So, think about the gas that comes out of a rocket. It has a mass and it has a velocity. But the gas was at rest. Therefore, its momentum changes. That shouldn't be an apostrophe. This, together with Newton's third law and Newton's second law, will allow us to calculate the up force, that is the thrust. Now, I'll explain this now. Let me open this. So, whoops. Okay. So, say you have something like this, and there's a gas inside, and the gas is first at rest. Okay? Then some of the gas shoots out. How much? Let's say a small amount. Let's say delta M. So for example, if this was, I don't know, let's just say 10,000 kilograms, then maybe the delta M is 2 kilograms per second. So we'll say 2 kilograms per second. Yeah? And usually it's per second here. So, if you want, you can say that's delta M over delta T, but I'll just write it like that, delta M. 2 kilograms per second. Okay. So let's imagine, here's the gas here, there's the 2 kilograms. First it's at rest, and now it's not. So what was the change in its momentum? Well, that would be mv minus mu. The m is 2 in this example. And the v is, in this example, it's going to the left. I have to give it a speed. So I'll say that the speed, we'll just say v is minus 100 meters per second. So here it'd be minus 100. Okay? And then minus, and the u? 0. So this is minus 200 kilogram meters per second. Okay? But do you remember the picture I gave you with the balloon? Do you remember that picture? If the gas is coming out the back, what will happen here? This will move forward, and this is because of Newton's third law. Action has a reaction. Okay? And not only that, the action here will equal the reaction here. So what I can do, that's delta P. I can divide both sides by delta T. But in this question here, how big is delta T? It's per second. It's 1 second. So that's divided by 1. But what is delta P over delta T? Force. So this force here, this thrust, will be the same as this force here that the gas experiences. So you end up saying the thrust is plus 200 newtons. So let me just summarize this nice and neatly for you. So if you have a rocket and it has a gas in it, and let's say the gas ejects at m kilograms per second, and the per second is important, with a speed of, let's say, v meters per second. And I'm just going to actually highlight it's very important that this is per second. Then the T here, the thrust, is given by the very simple formula mv. Now, again, it only works if everything is in the units of per second. So this is a very nice application of momentum. It can give you the force that rockets have when they eject their gas. Yeah. If you don't want to get confused, what you could do is put a little g here, the mass of the gas and the velocity of the gas. So you can write little g's here if you want. And this is the thrust of the rocket. So I think it'd be good if you write this down, this screen. Yeah?
Sorry, why is the gas in kg per second? The mass of the gas in
Yeah, the mass of the gas.
kg
Yeah.
per second.
The mass of the gas being ejected per second.
Okay, okay.
Alright, you got that? Yeah. Okay. So, very simple, it'll only take you a few seconds. At the launch of a large rocket, the hot gas is propelled at a velocity of 4462 meters per second. In each second, 7,485 kilograms of gas is burnt up and ejected. What upward force is provided by this release of hot gas, I should say? So, calculate the thrust, please. It should be pretty big. You got it? What you get? Big number, isn't it? Is it millions? Mega? Yeah. So about 33 mega newtons. Yeah? Multiply the two. Okay. Now, here's a very hard question. It was on the exam many years ago. It was a windy day and a physics student was walking home. The student stopped for a moment to calculate the force he is feeling from the wind. The wind was blowing at a speed of 12 meters per second into the stationary student. The student is 1.6 meters tall and on average 40 centimeters wide. The density of air is 1 kilogram per meter cubed. What is the force felt by the physics student due to the wind? Now, I'll let you try this for a minute. It's quite difficult. But my tip is, this is a lot like the rocket question, except instead of hot gas coming out of the rocket, in this one here, it's cold air being blown at the student. But the idea is the same formula. So if you could work out how many kilograms of air hits the student per second, then you basically have the problem solved. Because you just need to multiply that answer by 12 and you have the force. Okay? So once you get the idea, it's not too bad. Let's see if you can do it. I'll give you a minute. Okay. Have you got answers? Some of you are looking confused. Some of you are looking very confused. Let's have a look. You're looking confused. Right, so here's the student. How tall is the student? And how wide? 40. So there's the student there. 1.6 and 0.4 meters, okay? So we need to figure out how much air hits the student in 1 second. How fast is the wind moving? 12. So that means in 1 second, the wind, which is the air, which is 12 meters in front of him, all of this air here will hit him. It can't be more than 12 meters because the wind's not going fast enough to have more than that hit him. So if the wind's going 12 meters per second, it means basically per second 12 meters of air gets pushed into him. Okay? And how fast is this going? Sorry, we know how fast it's going, it's 12. The density, I said, is roughly 1 kilogram per meter cube. So look, let's calculate the mass here. Density is mass over volume. So mass is density by volume, which is roughly volume here because the density is 1. And the volume is 12 by 1.6 by 0.4. So according to my rocket formula, F will equal the mass of the gas times the speed of the gas, which will be 12 times 1.6 times 0.4 times 12, which equals 92.16. So 92.2, is it? So that is the force he will experience from the wind, 92 newtons. That's how much force he feels from the wind pushing against him. Can you see me?
Sorry, what's the velocity?
12. Okay. You got that? Yeah. Yeah, you got that? Yeah. Let me just fix those two typos. There was another mistake. Okay. Right. How many? Oh, a lot of questions. 13, wasn't it? Yeah. Okay. I'll let you start those for a few minutes, and then we'll go on to the next lesson.